All right, so this lesson is about observation and measurement. What you want to do is get your yellow notes out. What I'm covering on the board here is exactly what's on your notes. So I realize you may have difficulty seeing this. That's why I put it on here as well. So if you just follow along, you'll learn all about observation and measurement. All right, so observations in science, we always want to collect data. And to collect data, you have to make observations. And how you go about making observations is you use your 5 senses to make observations. So your senses include seeing things, sight, hearing things, sound, touching things, smelling things, and tasting things. Now, us as humans, we use some of these senses more than other ones. We probably get most of our information by our sense of sight or possibly our sense of hearing. Other animals get their information differently. Like moles, right? Moles in the ground, they really don't see anything, so they rely more on like smell and like feeling, all right? So there's other animals out there, worms, like worms really don't see, they use other senses as well. But us as humans, we use primarily seeing and hearing to get information. Now, sometimes if you lose one of your senses, sometimes you train one of your other senses to be a little bit better, kind of pick up the slack. So, for example, if you're blind, you might learn how to read in Braille, where there's little bumps on paper to represent letters. Now, for me, if I run my fingers over Braille, it really just feels like a bunch of bumps. It really doesn't mean anything to me. But to someone who's kind of trained their sense of touch to be a little more sensitive, they can run their fingers over the Braille and they can distinguish the little bumps as being different letters. In the schoolrooms here, we use the numbers right outside the room. Like my room's 132. If you've never seen Braille before, like right underneath the number is the number written in Braille too. So when you're in school, you can try to experiment and see how Braille feels. Or there's a news story about this kid who had cancer in his eyes and he lost his eyes. And what he was able to do is he was able to make these clicking sounds, and he could hear the sounds bounce off objects, and then from the echo coming off the objects, he could figure out where the objects were, just like a bat. That's how bats use echolocation. So he'd walk around going, and from the echoes coming off that, he could figure out where objects were. So that'd be an example of training one of your other senses to kind of take the place of the one that you lost. All right. Now, sometimes our senses aren't good enough for what we need them to do, and their senses need a little bit of help. So, for example, if we were looking at something that was very small, we might use something like a telescope or a microscope to help us see it. All right. When we use an instrument when we use a device to help our senses, we call that an instrument. So an instrument's a device used to aid your senses. So a microscope's a good example of that. If you're looking at something very far away, you might use a telescope or binoculars. At night, when everything's black, you might use infrared goggles. For your sense of hearing, if you wanted to hear better, you might use a hearing aid, or there's these things called sonic ears, which make it so you can hear better. For your sense of touch, an example of something you can use to help with your sense of touch would be like a cane. All right. Now you think about using blind people as an example again. If they're walking down the street, they use a cane and they kind of feel around in front of them with the cane. That way, if they stumble upon something hard, they can kind of feel how big that object is and how hard it is and so forth. What they're doing with that stick is basically extending their sense of touch. So a cane would be an example of that. Or another example of an instrument would be for like skiers up in the Alps or the Rockies, let's say there's an avalanche and somebody gets buried in the snow. How they go about locating someone buried in the snow is they have these long rods, and they have like a whole bunch of people lined up in a row with these long rods, and they take the rods and everyone jams the rod in the snow, and if they don't hit anything, everyone takes a step forward, jams the rod into the snow. They don't hit anything, everyone takes a step forward, jams the rod into the snow, and then when they eventually hit something, that's when they'll start digging to look for a body. But if you think about what you're doing, you're using that stick to extend your sense of touch into the ground. All right? So those are examples of instruments where you use an object or device to help out your senses. All right. Now, let's say you make a bunch of observations. What do you do with them? All right. Well, what scientists like to do with observations is they like to make inferences about these observations. And what an inference is an interpretation or conclusion based on your observations. Predictions are an example of inferences. Now, let's give you an example. All right, let's say you're sitting home one time and all of a sudden you hear on the door. All right, you go to open the door and there's a guy with a box like this. Guy's got a box and he's like, delivery for 12 Main Street. And I'm like, well, yeah, it's my address, 12 Main Street. I didn't order anything though. And the guy's like, says right here, 12 Main Street, it's all paid for, and he gives you this box. All right. Now, I didn't order it, so I don't know what's in it. So I have this mystery box. All right. Now, if I want to find out what's in the mystery box, what I might start to do is I might start to make observations about that box. And so what I would do is maybe first I feel the bottom of the box and I feel that the box is warm. All right. So I'm using my sense of touch. Another thing, maybe I feel the weight to the box. Maybe the box weighs about a pound or so, roughly. And so again, that's my sense of touch. All right. Another thing, I look at the box and I see the box is a relatively square box. It's relatively flat box. So I'm using my sense of sight. All right. Next, maybe I move the box around a little bit like this, and I hear something kind of big slide back and forth. So using my sense of sound or my sense of hearing, I can tell it's not like a bunch of little things rolling around. It's like one big mass. And then maybe I smell the box, and I could smell the oregano and tomato sauce and cheese and stuff like that. Now, I haven't opened the box yet, so I don't know exactly what's in the box, but I've made a bunch of observations. So I've looked at the box and I see it's a square box. The sound, I'm kind of shifted around. I can hear what the sound of it sounds like when it slides. My sense of touch, I can feel the bottom of the box. It's warm and it weighs about a pound. And it smells like tomato sauce and cheese. But again, I don't know what's in the box because I haven't opened it yet. Now, what I can do with that information is I can make an inference about what's in the box. So a logical inference I could draw would be that inside the box is a pizza, right? Because the pizza would have met all those criteria. I don't know for a fact there's a pizza in there, but based on those observations I made, it would make sense that there's a pizza inside this box, all right? Now, I open up the box, maybe it's not a pizza, maybe it's a stromboli, or maybe it's baked ziti, or maybe it's a calzone. There's other things that would have been a logical inference from those observations. Now, my inference that there was a pizza, let's say there was a calzone in the box, all right? My inference that there was a pizza in the box would be a logical inference, but it wasn't right, all right? So sometimes that's what happens with scientists quite a bit. You might have two scientists looking at the same set of data, but they might draw different inferences or draw different conclusions from it. You know, one person from all those observations may have thought it was a pizza, another person may have thought it was a calzone based on those observations, but again, you don't know exactly what's in the box until you open it up. And only one of those two people is probably going to be right. All right. So that's an inference. All right. Predictions are examples of inferences, like a weatherman. You know, he makes a weather forecast. You know, he's making observations about the wind direction. That's an observation. He might look at the clouds. That's an observation. He might look at a radar image. That's an observation. And then from those observations, he makes a prediction of what tomorrow's weather is going to be like. All right, so those are inferences. All right, another thing that can be done after you make a bunch of observations is you can classify things based on those observations. All right, so classification is grouping together things in a meaningful way based on similar properties. All right, so you find similarities between objects or between things, and then you put them in groups based on those similarities. So a real simple example right over here, let's say I have these 6 materials right there. I got water, wood, oil, alcohol, steel, and plastic. All right. Now, you know, those are 6 materials that you should be somewhat familiar with. Now, I'm kind of visualizing those materials in my head right now, and I'm going to classify them and put them into 2 groups. All right. So on one side, what I'm going to do is I'm going to put water over here. I'm going to put wood over here. All right. I'm going to put oil over here. I'm going to put alcohol over here. I'm going to put steel over here. I'm going to put plastic over here. Okay. Now, so these are all things, objects I'm familiar with. I've made observations about these objects before in my life. From those observations I've made before, I've put them into 2 groups. I put these in one group, those in one group. Now, if I had to, so what property was I using to break them down by? So if you look, give you a couple seconds there to look at that. So water, oil, alcohol over here, wood, steel, plastic over there. All right. So the property that I classified them according to would be their phase of matter. Right. So all these materials here were all normally liquids. All right. All the materials right there are normally, you know, at regular temperatures and stuff, are a solid. So these are the objects I was familiar with, and they categorized them and broke them down into 2 groups by a particular characteristic that they shared. All right. So grouping things based on similar characteristics is known as classification. All right, now, sometimes when I make an observation, I need to be more specific, all right? And what I mean by that is like just describing something as being long would not be a good enough observation for it. Because if I said, I was at this meeting and the meeting was very long, all right? Well, some people, a long meeting might be 5 minutes. Other people, a long meeting might be 15 minutes. Other people, a long meeting might be 2 hours, all right? So, to make observations more precise, what we use are measurements, all right? Now, measuring is a direct comparison to a known standard. So when I'm describing how long something is, I want to tell someone the length compared to something that we're all familiar with. Now, back, in times of cavemen, all right, there might have been, Grog the caveman might have gone out there and killed a woolly mammoth, all right, and maybe needed some help to bring the meat back to his tribe. So, and he wanted to go back to his tribe and tell them how big this woolly mammoth is. All right. Well, he doesn't carry a lot of stuff with him. You know, it's not like the caveman's carrying around a tape measure with him. But if he wanted to describe how big that woolly mammoth was, what he could do, and what the early units of measurement were based on, is parts of the human body. All right. So, like, if the woolly mammoth was like this big, he might say, well, it was 1, 2, 3 paces long. So when he goes back to his tribe, he can say, hey, I just killed this woolly mammoth. And they're like, how big is it? It was 3 paces long. And people know how big the guy's paces are roughly, so that everyone has an idea of how big that woolly mammoth is. All right. A lot of the early units of measurement were based on parts of the human body. So a foot, yeah, you're probably familiar with. The foot was originally based on a human foot. A unit for measurement, the cubit, from there to there. Right? Noah's Ark was supposed to be X amount of cubits long. Also, a yard, an old yard, was the distance from the tip of your nose to the tip of your finger right there. All right? So a lot of the early units of measurement were based on parts of the human body. Now, it doesn't take a rocket scientist to figure out what the difficulty with that is. Is that people are different sizes. So your foot and my foot aren't necessarily going to be the same size. So as a result, there need to be some sort of standardization. And what a lot of early countries would do is, whatever the king's foot, size of the king's foot, that would be an official foot. All right. Well, that's all fine and dandy, but a foot in one country had one king, another country would have another king with a different size foot. So even though everything might be the same in one country, in the other country, their feet would be different than our feet. One of the myths out there, this is kind of the result of that, would be like the height of Napoleon. Like normally when you hear Napoleon, I think he was like really short. The reason why he's actually about 5'7" or so, which at the time was about average height. The reason why he was thought to be short is because at some point his height was given in inches, and a French inch and an English inch were actually different sizes. So when the height was given in inches, the English heard how many inches and just assumed he was short, but it was actually French inches were actually a little bit bigger, but anyways. So there's problems there, you can see the problems. Now, to help solve that, what happened is scientists and governments and stuff, decided to come up with a uniform unit of measurement that people can use throughout the world. And the system they came up with was the metric system. And the metric system is very handy because it's base 10. So converting from one unit to another is just a matter of moving a decimal point. So there's like 10 millimeters in a centimeter, 10 centimeters in a decimeter, 10 decimeters in a meter, and so forth. Which is much easier to do than converting with the units we use, which are English units, 12 inches in a foot, 5,280 feet in a mile, 1,760 yards in a mile, yada, yada, yada. It's a lot more difficult. Metric system is much more easy to use. Pretty much the whole world uses the metric system. And then back in like the 70s and 80s, there was a big push to get the United States to use the metric system as well. And to help kids learn the metric system, they even had things like this. This is the Exciting World of Metrics lunchbox. So kids could eat their lunch and study the metric system by looking at their lunchbox. And it tells you a centipede has 100 legs, because centa means 100. Or, let's have on here. A millipede has 1,000 legs, because milli means 1,000 and so forth. All right. But for whatever reason, it didn't really stick. And so there's only like 2 countries in the world that don't really use the metric system too much, and we're one of them. But the metric system is much easier to use. And this class, we're almost always going to use the metric system. There's a little bit of stuff with mapping where we might still use feet and miles, and maybe a little bit with weather, because a lot of temperatures are still given in Fahrenheit. But pretty much everything we do is going to be using the metric system. All right. Now, there's different standard units of measurement. Some of the basic units, if you're measuring length, the basic unit is a meter, or some variation of the meter, centimeter, millimeter, decimeter. For mass, the basic metric unit for that's the gram, kilogram, milligram, so forth. For temperature, the metric unit for that is degrees Celsius. So with 0 being when water freezes and 100 being when water boils, as opposed to 32 and 212 in Fahrenheit. And time, now time's, we use seconds and minutes and so forth. Time's not really metric, and that time's not dividable by 10. There really isn't a metric time. The reason why there's like 60 seconds in a minute and 60 minutes in an hour is because 60 is a number that you can divide by a bunch of times and not have to have decimal points. Because like 60 divided by 2 is 30, 60 divided by 3 is 20, 60 divided by 4 is 15, 60 divided by 5 is 12, and so forth. So it's a number that works out well because you can cut it up in a bunch of time without having to deal with decimals. All right, so those are basic units. Another type of unit you can have is a derived unit. And a derived unit is when you combine 2 or more other units and you put them together to make a new unit. And probably the one that you're most familiar with, it's not a metric unit, but it's probably the one that you're most familiar with, is the unit that we frequently use for the speed of cars, miles per hour. All right, now you think about what miles per hour means. Miles per hour is miles, which is a length unit, divided by hour, which is a time unit. So it's length divided by time. You're taking a length unit and a time unit, putting them together to come up with a unit for speed, miles per hour. Or another example of derived unit would be volume. All right. Now, if you think about volume, the metric unit for that's cubic centimeters. All right. Now, if you think about what that really means, a cube has 3 sides to it. It's basically this length, and this length. So it's 3 length units put together is how you get your unit for the size of something, volume. And there's 1,000,001 other derived units you can come up with. If you might say the temperature went up 12 degrees per hour, right? Degrees per hour would be another example of a derived unit, right? So basic units stand on their own. Derived units are where you take 2 other units and put them together. Now, all this talk about measuring makes me want to measure something. So let's say I want to measure the length of this ruler. All right. Now, I take a meter stick out really quick, and I measure the length of this ruler, and I do it really fast, and I end up with a measurement of 23 centimeters. All right. I measured this stapler to be 23 centimeters long. All right. Now, I go home at night, and I think, I really didn't spend a lot of time measuring that stapler. I wonder how long it really is. So what I do is I look up the company that makes these staplers. It's Charles Lennard Incorporated out of Hapog, New York. And there's an email address on there. It's item number 82415. So I emailed the company and said, yo, I have this stapler here, and I want to know the exact dimensions of the stapler. So they look on the blueprints, and they tell me the stapler actually is 20 centimeters long. All right? So I measured it to be 23 when the acceptor to the actual value is 20. All right? So my measurement has some error in it. Now, is 3 centimeters worth of error big? All right, well, sometimes it is, sometimes it's not. If I'm measuring the distance between Clifton Springs and Rochester, and my distance was off by 3 centimeters, it's not a big deal. If I'm measuring the length of this pen cap here, all right, now it's off by 3 centimeters, That's a pretty lousy measurement. So to better describe our measurements and how good our measurements are, we use something called percent error or percent deviation. It's a formula that lets us know exactly how good our observations are. All right. So the formula is in your note sheet there. The formula is the difference between the measured and accepted value over the accepted value times 100. All right. So I'm going to do the percent error problem right here. All right. So difference between the measured and accepted value. So I got the measured value of 23 and the accepted value of 20. So what I want to do is I'm going to do the bigger number minus a smaller number. So it's going to be 23 centimeters minus 20 centimeters on top. All right. Over. All right. The number that goes in the bottom is the accepted value, and that's the number that when I emailed the company, they told me it was exactly 20 centimeters long. All right. So 20 centimeters goes on the bottom. All right. And that whole thing is times 100. All right. Now I simplify this. 23 minus 20 is 3 centimeters. All right. Over 20 centimeters times 100. Okay. Now, I take out my calculator. I go 3 divided by 20. The number I'm going to get in my calculator is 0.15. All right. Now I have to take that, and I'm going to take that number and multiply that by 100. All right. So 0.15 times 100 is going to work out to be 15. Now, as far as the units go, all right, a common mistake people make on these is they'll write centimeters down for a unit right there. But when I take centimeters and divide them by centimeters, they actually cancel each other out. So there's no units anymore. So when I do 0.15 times 100, I just have 15, and what that is 15%. All right. So that's how much error there was in my measurement. My measurement was off by 15%. All right. So that's how you do a percent error problem. The difference between the measured and accepted, the bigger one minus the smaller one, over the accepted, whole thing times 100, and that gives you percent error. Some common mistakes people make with these. One of them is that, let's say when you got to this point here, 3 divided by 20, you always want to type in your calculator the first number divided by the bottom number, the top number divided by the bottom number. All right, you're going to get a decimal. All right, that's okay. So it's 3 divided by 20, not 20 divided by 3. All right. Now another thing you want to make sure that you do 3 divided by 20, hit equals, and then multiply it by 100. All right, 3 divided by 20, hit equals, and then multiply it by 100. And again, it's not centimeters, it would be percent over here. All right. Now, another thing, as far as how long I should take that number out, because sometimes if you did like 1 divided by 3, it'd be like 0.333333, you know, repeating. Usually, you know, if I did this to the nearest 10th or the nearest 100th, in most cases, that's fine. You're not going to impress me by writing out a gazillion numbers in there with the decimal point. So with these, if you did it to the 100th or 10th, one of those, it's usually good. All right. So on your paper, on the back there is a couple more examples for you to do. And then you also have a paper, a white paper, it says percent error problems on top of it. And you have those problems to do as well. So how you would solve them, again, is just using that formula, and you do it the exact same way I did right here. All right, so that is observation and measurement.